We can't just pick up the Earth and dump it on a set of scales to find its mass. For a start, where would we put those scales? And what gravitational field would we use to get them to work? Likewise, we can't just use a tape measure to measure the radius or the circumference of the Earth. Well, some things have been known for a very long time, and you'll be impressed with how they were figured out. So stay to the end to get the full story and find out why these measurements are so important. Our story begins in ancient Greece, around 240 BC. The Greek mathematician Eratosthenes made the first known measurement of the Earth's radius. He was a polymath, being also an astronomer, a musician, and a poet. He was also aware of the curvature of the Earth. Eratosthenes was appointed as the chief librarian in the great library in Alexandria. Whilst there, he was able to access results, and he learned that a stick stuck in the ground in the city of Cyan, now Aswan in modern Egypt, during the summer solstice, the stick cast no shadow. The story goes that the sun actually lit the bottom of the well in the city centre because the sun was directly overhead. Eratosthenes noticed at the same time, though, a stick stuck in the ground in Alexandria would cast a shadow. So with the knowledge of the distance between the two cities and knowing the fact that they're both on more or less on the same meridian, so at the same time, he was able to use the angle of the shadow cast by a stick at Cyan to calculate the circumference of the Earth. I could quickly show you how he did that with this map here. Here's a stick that I'm going to stick in Alexandria. And during the equinox, when the sun's directly ahead, there is no shadow. And I can show you that. And with the rare thing in the sky here, certainly in the UK, the sun, there we are. There's no shadow when I point it directly at the sun. At the same time of day, if the Earth was flat, obviously, don't want to say anything controversial. So when the sun's directly ahead, there we are, no shadow on both sticks. But the Earth isn't flat, it's curved. And there we are. If I curve the Earth, there we go. So now when there's no shadow at Alexandria, with the curved Earth, there is a shadow down at Cyan. Using this idea, Eratosthenes realised that if he measured the angle from the tip of the stick in Alexandria to the tip of the shadow, he would have the same angle as he would have in the centre of the Earth mapped out from Alexandria all the way over to Cyan. He worked that out to be about a 50th of a circle, or 7 degrees if you like. He also knew the distance from Alexandria to Cyan. He knew it was 5,000 stadia. So if he multiplied that by 50, he got the circumference of the Earth. Eratosthenes' estimate was remarkably accurate. It was around about 40,000 kilometres, which is more or less the same as we think it is today. Eratosthenes' books and writings have long since been lost, but it's known that he went on to produce the first maps that allowed for the curvature of the Earth and showed lines similar to those on modern maps depicting the lines of longitude and latitude. By many, he is considered the father of geography and is thought to be the first to use the word geography. If that wasn't enough, Eratosthenes calculated the axial tilt of the Earth with remarkable accuracy. After the fall of the Roman Empire, much of the knowledge, the scientific knowledge gained by the Greeks, was preserved and expanded upon by Islamic scholars during the Middle Ages. One notable figure was Al-Biruni, a Persian polymath of the 10th and 11th centuries. Al-Biruni used his skills to calculate the radius of the Earth. To do this, he had to find a mountain and calculate the height of that mountain. In this diagram, you can see that Al-Biruni needed to measure the distance from the base of a mountain to 2 points A and B. He then measured the angles made to the top of the mountain from those points, alpha and beta. From there, he was able to calculate the height of the mountain. I will only briefly mention the maths, but it is worth doing. But if you're not interested, just skip forward 20 seconds or so. H equals sine alpha from the triangle OAM. In triangle AMB, gamma equals alpha minus beta. And we can apply the sine rule to show that S over sine beta equals D over sine alpha minus beta. Substituting in for S, we can get H equals sine alpha sine beta over sine alpha minus beta, all multiplied by D. And so H equals tan alpha tan beta multiplied by D over tan alpha minus tan beta. which is still being used in surveys to the present day. Once he had the height of the mountain, he was now able to use the angle that the horizon seemed to dip to calculate the radius of the Earth. In this diagram, you see that a right-angled triangle is formed, and so the trigonometry is straightforward. Cos delta equals A over A plus H, and so A equals H cos delta over 1 minus cos delta. It's claimed that Al-Biruni was able to calculate the radius of the Earth to within 2% of the current accepted value. Despite his genius method, that does seem unlikely. Similar to Eratosthenes, Al-Biruni used the units of cubits, so cubits from your elbow to your tip of your middle finger, but we're unsure exactly what measurements they were using. It is also difficult to understand how Al-Biruni measured the distance accurately from the base of the mountain. One of the biggest factors affecting his result will be the refraction of light in the atmosphere, which he would have been unaware of. None of this is to take away the cleverness of Al-Biruni. Incredibly, in some of his writings, he predicted the presence of a very large landmass somewhere between Europe and Asia, long before the discovery of the Americas. The age of exploration in the 15th and 16th centuries further refined our understanding of the Earth's size. Explorers like Christopher Columbus and Ferdinand Magellan provided practical evidence that the Earth was round by sailing round it. Magellan's expedition, which completed the first circumnavigation of the globe, provided evidence of the Earth's roundness and a good feeling for its size and geography. This era also saw improvements in navigation tools like the astrolabe and later the sextant, which helped sailors measure latitude by observing the stars. In the following 17th century, Sir Isaac Newton proposed a revolutionary idea. The Earth was not a perfect sphere, but an oblate spheroid, bulging at the equator due to its rotation. Newton's theory was confirmed by expeditions to the equator and closer to the poles in the 18th century, which measured the changes in length of a degree of latitude. These measurements showed that the Earth was indeed flattened at the poles and bulging at the equator, validating Newton's predictions. So that's the history of how we first measured the dimensions of the Earth. What about the mass? In the late 18th century, Henry Cavendish conducted what is now known as the Cavendish experiment. Using a torsion balance, he measured the gravitational attraction between lead spheres. By observing the tiny forces on the masses, Cavendish was able to measure the universal gravitational constant, G, building on Newton's work on universal gravitation. With this constant, scientists could then calculate the Earth's mass using the formula for gravitational force provided by Newton. From Cavendish's work, we know the mass of the Earth to be around about 5.97 times 10 to the 24 kilograms. This experiment was pivotal because its result, G, links gravitational force to the mass of the Earth and other celestial bodies. G remains one of the least known physical constants, and we still only know it to a handful of significant figures. Today we have advanced technology which has refined these measurements. Satellites like the GRACE mission, Gravity Recovery and Climate Experiment, provide precise data on Earth's gravitational field. GRACE and similar missions use changes in the Earth's gravitational field to measure the distribution of mass within the Earth, including changes in ice sheets, groundwater storage, and ocean currents. These measurements are incredibly precise and provide insights that were unimaginable a few decades ago. Using data from these satellites, we can accurately measure the Earth's volume and density. The volume is about 1 trillion cubic kilometres, and the average density is roughly 5.52 grams per cubic centimetre. This data helps us understand not only the Earth's size, but also its internal structure and composition. Maybe I'll do another video on the structure of the Earth, because that's a fascinating topic all of its own. Understanding the Earth's size, mass and density is crucial not just for academic purposes, but also for many other applications. These measurements help in predicting natural disasters, understanding climate change and exploring natural resources. For instance, the accurate measurements of the Earth's gravitational field can help predict volcanic eruptions and earthquakes. They also improve our models of sea level rise due to melting ice sheets, which is critical for understanding the impacts of climate change. Our quest to measure the Earth reflects our ongoing curiosity and desire to understand the world that we live in, including this flipping weather. Each step from ancient observations to modern technologies brings us a tiny bit closer to understanding our planet's complexities. But don't move down south for the weather, whatever you do. It's always wet or windy.